In section 2.6, we're going to cover a topic called related rates. Related rates are an application of the derivative, and what we're going to have is rates that are changing over time. And so you can see why this would be applicable in real life, because basically everything's changing over time, and related rates deal with the rate, like miles per hour or feet per second, gallons per minute in an oil tank or something like that, that things are changing. So on the bottom for related rates is always dt, because that's what's changing constantly in life is time. So what we've got is just, first of all, just a little explanation of how you write these rates in our formal notation. For 1a, it says John is growing at the rate of 3 inches per year. Because he's growing, we'd have what we would call a positive rate, and we would say maybe dh for his height. The change in height over change in time is equal to a positive 3, and that would be 3 inches per year if I were to label that. Likewise, if my mutual fund is shrinking means going down, so I'm going to have a negative rate, and that's money, so I might want to say dm dt is equal to negative 0.04 cents per day. The radius of a circle is increasing. We're going to have a lot of geometry problems with this, with cones and spheres and stuff like that that's changing. And the radius of a circle is changing, increasing at a rate of 4 feet per hour. So we'd say dr dt is equal to 4. And likewise, the volume of a cone is decreasing. So we'd say the change in volume over change in time is decreasing. So we'd say that's negative 2 cubic inches per second. Which leads us to we're going to start off with the very easiest of geometry figures, the rectangle. It's a 10 by 6 inch rectangle. So we've got a length of 10 and a width of 6, and the sides are changing over time. And we're to write formulas for perimeter and area, and then how fast each is changing. So first of all, with our perimeter of a rectangle would be 2 lengths plus 2 widths. Our change in perimeter we'd call dp dt, the change in perimeter over time. And what we'd have to do is take the derivative or the change in our formula for perimeter over time. And then this is the most important part. You have to kind of deal with this. This is chain rule. This is implicit differentiation. It's kind of like when if you had d2y dx, and you'd say, well, that's not a variable match. We consider y a function of x itself. So we do 2, and then we do dy dx, which in our implicit we call 2y prime. But for related rates, we're going to keep that formal notation going, because that's what we're looking for, is changes over time. So when I'm taking the derivative over here, what I've got would be 2 dl dt plus 2 dw dt, or 2 times the change in the length over time plus 2 times the change in the width over time. Likewise, for area of a rectangle is length times width. So when I find my change in area, I'd call it dA dt, which means I do the change in time of length times width. Now again, this is a product, so I'd use product rule, but I also have to notice I don't have a variable match, so it's like a chain rule. So what that becomes over there on the left-hand side is the first times the derivative of the second with respect to time, plus the second function times the derivative of the first with respect to time. And then if they give me values, for example right here, where it says the length and the width are decreasing at a rate of 2 inches per second, and I am supposed to evaluate that, well, then I go back to my original, that my length is 10 and my width is 6, so I'd say 10 times, and my width is changing or decreasing at a rate of negative 2, plus its original w is 6, and that's also changing by negative 2. So I'd end up on that one with negative 32. And that would be, because we're talking about area, that would be inches squared per second. All right? So really what these involve is things changing over time. And I'm not going to go through any more of these numerical ones. I want to move on and sketch out on the next page here So I've got a ladder falling down a wall, and I'm going to go draw this picture right here. So here we've got a wall, and I've got a ladder. And the ladder is what we'd call a constant, because even though the ladder is falling, it won't be changing with respect to time. So I've got a constant right here for my ladder. I've got a length across the bottom, which I'll call x, and it's moving away from the wall. So we would say that we've got a rate of change of x as it moves away from the wall. We've got a rate of change of y as the ladder moves down the wall. So when it says what is changing with respect to time, on this picture there's two things. X is changing, or the distance along the ground right there. So we'd see dx dt. That would actually be a positive number because it's getting bigger, or I'm moving away. We also have y that's changing over time, and we'd say that's a negative because this is moving down or getting shorter. We call L the constant. So when it says which rate is negative, we would say dy dt because it's getting closer to the start, not farther away. So it says to write an expression which relates the three variables and take its derivative with respect to time. So what we've got going here is Pythagorean theorem relates these variables. There will always be some relationship between the variables in the word problems. If we're talking about area of a circle, we've got pi r, a equals pi r squared. On this one, we've got the Pythagorean theorem. We'll have a lot of geometry problems that deal with cones and cylinders and such. You don't really need to memorize those formulas. Those will usually be given to you. But the Pythagorean theorem is one that you should definitely know. So I'm writing an expression where x squared plus y squared would have to be L squared. That's the relationship. Now what I'm going to do is I'm going to take the derivative, which basically means I'm going to start this ladder sliding down the wall. I'm going to start the clock ticking, and I'm going to start the ladder moving against the wall, which would be the change in time would equal the change in L squared over time. Now, the change on this side, the ladder is constant, so the change in the length of the ladder is obviously going to be 0. That kind of goes with our constant rule that the derivative of a constant is always 0. Regardless of what, maybe if the ladder was, say, 10, then this would have been a 100. Its derivative is always going to be 0. You might say, well, why can't I do 2L dL dt? You could, but this isn't changing, so the ladder's length isn't, so that would be a 0. And then on the right-hand side, I'd have the derivative of x squared with respect to time, plus the derivative of y squared with respect to time. And again, I don't have a variable match, so I've got a chain rule reaction going on. The derivative of x squared with respect to x is twice x, but then I have to do dx dt. So really what I'm doing is this, the derivative of x squared with respect to x times the derivative of x with respect to t. And this is 2x. It's a chain rule that's going on here. Plus on the y side, I'd have 2y times dy dt. All right? So with the ladder, that's what I would have. Now it says, change x and y to be an h for base and height. So now we're going to consider maybe it's an area of a triangle. Instead of the ladder sliding down the wall, I'm going to talk about the area of this triangle. It says, write an expression for the rate at which the area is changing. So again, I need a relationship between the variables. The relationship is area is equal to 1/2 base times height. And it says, write an expression for the rate. That means I'm going to be taking a derivative that the area of the triangle is changing. So when I take the change in area over time, the rate at which the area is changing, that has to equal the derivative of 1/2 the base times the height, changing over time. And again, I could quit right there, but if I wanted to clean this up, I'd say, well, I've got the 1/2, the constant multiple rule that can come up front, and then I have the derivative of the base times height with respect to time. And then I'd use the product rule on this, and I would have an expression for the area of the triangle. So on the next page, again, we've got another situation. I'm just trying to get you to used to the situations, and we've got rates of change. I'm going to have this be a cylindrical pool. We don't see a whole lot of cylinders you'll see why, but just for this one, we'll have a cylindrical pool. It's got some water in it. The water's leaking out. So there's my sketch. My pool has dimensions. It's got a radius of r, which is important, and I've got a height h, and then I've got the height of the water here also. So when it says what is changing with respect to time, well, there's two things here that are changing. As the water leaks out, the height of the water is going down. So I would say the height of the water. And what I would call that would be dH dt. And notice that's going down, or the number's getting smaller, so that would actually be a negative rate of change. Also changing with respect to time is the volume of the pool. So the volume, or the change in volume over change in time, is also going down. So I have two things that are changing, the height of the water and the volume of the water. What's remaining constant in this problem would be the radius. The radius does not change as the water leaks out. Now, had it been a cone, all right, then the radius is changing as we go farther and farther and farther down. The radius of the height of the water level right there would be changing, but for the cylinder it isn't. So it says write an equation for the volume of the pool. Well, volume of a cylinder is pi times the radius squared times the height. Okay, and that actually should say volume of the water in the pool. To be honest with you, that would be a better use of that. All right, so it says take the derivative with respect to time. So this is what I've got. The volume of the water is pi times the radius of the pool squared times the height of the water. It's a geometry formula for volume of a cylinder. What I'm now going to do is start the clock ticking. What I mean by that is I'm going to take the derivative of both sides with respect to time, and they obviously have to be equal because they are equal expressions. So I'm going to take the derivative of both sides with respect to time. So what happens here is, on the right, I get dV dt, change in volume over time, is equal to pi times dr squared h dt. So that would go right here. Pi can come out front because it's a constant. Now, on the right-hand side, I've got a product rule going on here. It's r squared times h, plus it's going to be a chain rule. So watch how this works. I've got pi. I do first function, r squared, times the derivative of the second function, which we'd say is dh dt, plus I've got the second function, which is h, times the derivative of the first function, which would be 2r, but then I have to do dr dt. It's a chain rule, like when you did implicit. Now, what's interesting here is that because the radius is constant for the cylinder, dr dt is 0. And that's what I want you to remember for our little test tomorrow, is I want you to remember that when the radius, when I'm working with the cylinder, the one that's not changing is this radius. As the pool goes down and down and down, the radius of the pool does not change. So it's a unique situation where we get the dr dt is equal to 0. So this whole thing goes. And what I end up with is pi r squared dh dt. Now let's talk about this outside of all its calculus mess here. What this is saying is the rate at which the volume changes of that water as it starts to leak is a direct proportion between the area of the base, which makes sense because a bigger base, it's, you know what I mean, it's going to definitely affect the volume, times the rate at which the height is changing, which also makes sense. If it's a big hole and it's leaking fast, that'll affect the volume a lot. Or if it's a really small radius on the bottom, it also affects the volume. So this should kind of make sense to you right here. So that's all I'm going to give you for notes today. And what I would like you to remember is that the rate of change of the radius is equal to 0 on the cylinder. That's it. That's all I need you to remember. And we'll talk a lot more about this tomorrow. You guys have a good night.